All right, guys, so in this video, we are going to discuss entropy. We've already talked about enthalpy and the fact that enthalpy is a measurement of the heat exchange. We've talked about sign conventions with enthalpy, and we've also talked about the different ways to calculate enthalpy. Well, now what we're going to focus on is entropy. Entropy is given by the symbol delta S. It is a measurement of the dispersal of the matter and energy of a system. So, what I want to talk about first is show you the different laws of thermodynamics and how entropy is involved with these laws of thermodynamics. And then we're going to go into how do we predict the sign for delta S and then the calculations for delta S. So this should be a fairly quick video. If you look in your packet, you'll see three laws of thermodynamics here. So you have the first law of thermodynamics, which we've already talked about in our delta H discussion. So this says that energy can never be created or destroyed. So whatever energy we have in the universe is held constant. If you remember when we worked with our calorimetry problems, we said the heat of the reaction was equal to the negative heat of the water. The reason why is because the water, if it absorbed energy from the energy that was lost from the reaction. So whatever energy was lost in the reaction was the same amount of energy that was absorbed by the water. So it's just a transfer of energy that you have there. The second law and third law of thermodynamics we have not talked about yet. So the second law of thermodynamics says that the universe is constantly increasing the dispersal of matter and energy. So we got to think about the universe. We know that the universe is ever expanding. And because it's expanding, the dispersal of matter and energy is increasing over time. Well, that measurement of the dispersal of matter and energy, that is known as entropy. So, what the second law of thermodynamics is essentially saying is that entropy is increasing in the universe. Now let's look at the third law of thermodynamics. The third law says that the entropy of a perfect crystal at 0 Kelvin is 0. 0 Kelvin is absolute zero. Some pretty crazy things happen when you have absolute zero. The molecules that are moving around, they actually stop. They no longer have motion. Even solids have a little bit of vibrational motion. But at 0 Kelvin, all motion stops of those molecules. So only when you have no motion at all of a perfect crystal. So what that is saying is essentially the structure of that specimen is flawless. And that is a very, very rare thing to happen. So the entropy of a perfect crystal at 0 Kelvin, where there's no motion, is 0. What that law is essentially saying is that when we have free elements, they will have a little bit of entropy because those free elements, even though they're by themselves, there's still motion, whether it's motion of those molecules or whether it's a motion of those electrons constantly moving. This is different from when we were working with delta H in our Hess's law equations. Remember, delta H for the free elements were just 0 because we don't have to use energy to make those free elements. They're just naturally occurring. That cannot be said for delta S. Delta S for free elements will have some quantity because there is a movement of those molecules. So if anytime there's a movement, there is naturally going to be some dispersal of matter and energy. So if we go to the next page, down at the bottom of page 2, it says we can predict the sign of entropy. So whether or not entropy is increasing in a reaction or whether or not entropy is decreasing in a reaction. Anytime entropy increases in a reaction, you get a positive delta S value. So positive value means entropy is increasing over time. If you have a negative delta S value, what that is telling me is that the dispersal of the energy is decreasing in that particular reaction. So positive delta S, increase in entropy. Negative delta S, decrease in entropy. And we can figure out if there's an increase or decrease in entropy by looking at the particular states of matter. So what I have here is a little simulation to show you some solid. So we have some solid neon here, and you see how these molecules have movement. So even though it's solid neon, there will be some entropy there. There is some dispersal. But then let's look at a liquid. You see, you have more dispersal of that matter. And even a gas, you have even more dispersal of that matter. So if I have a reaction, I'm going to first look at my states of matter. If I'm going from the solid to liquid, or solid to a gas, or even a liquid to a gas state, then what's going to happen is my entropy is increasing, and that would be a positive delta S value. But if I went from a gas to a liquid, or a liquid to a solid, or even a gas to a solid state, what's happening there is my dispersal is decreasing. Therefore, my entropy is decreasing, and it would get a negative delta S sign. So when you're predicting your sign for delta S, the first thing you look at in that reaction is the states of matter. If I'm going to a more energetic state of matter, then entropy will increase. It will be a positive delta S value. If I go to a lower energy state of matter, then my dispersal will decrease. Therefore, my entropy will decrease, and I will have a negative delta S sign. Now, this also goes for things that I can dissolve in water. So you see this second bullet, actually it's the third bullet here. When a pure solid or liquid dissolves in a solvent, the entropy of the substance increases. So if I dissolve a solid in water, what you're doing is you have that solid state right here. And you're actually, this doesn't really show it, but you're actually showing movement of ions that are present there. And if I have ions that are moving around, then I have a greater dispersal of that matter. So therefore, my entropy increases anytime a solid or liquid dissolves in something. Now, if I have the same number, the same state of matter. So let's say we have something where a gas is in the products and the reactant side. So let me pull up something here to help us show this. So let's say we have N2 gas plus H2 gas, and that's going to NH3 gas. And to balance that equation, let's put a 2 right there and a 3 right there. And we want to predict the sign for delta S. So what we would look at is we would look at the states of matter. Now, it just so happens that all the states of matter are the same. So instead of looking at the states of matter, we now have to look at how many moles of gas we have on the reactant side and how many moles of gas we have on the product side. And to figure out, is there greater dispersal or is there a smaller amount of dispersal? And that will give us a sign of delta S. So 3 moles plus 1 mole is equal to 4 moles of gas overall on my reactant side. On my product side, I have 2 moles of gas. So what is going to be a greater dispersal of matter? Is it going to be 4 moles of gas, 4 moles of gas just dispersed all around here, or is it going to be 2 moles of gas dispersed around here? Which would be happening here? If I go from 4 to 2 moles of gas, am I going to increase my entropy or am I going to decrease my entropy? Well, the correct answer here is that I'm going to decrease my entropy when I go from a higher moles of gas to a lower moles of gas. And if I decrease my entropy there, I get a negative delta S quantity. So now let's look at these example problems here. Exercise 1, what we want to do is predict the sign for the entropy change and justify our answers. So for part A, we have solid sugar is added to water to form a solution. So if I bring paint back up here, let's look and see what's happening. Solid sugar, so we have a solid, is being added to water to form a solution. When I put that solid into solution, I now have aqueous things. And when the aqueous substance, what's happening there is you actually have these things that are just floating around. They're now mobile ions, and we have a greater dispersal of that matter. So, because of that, we have a positive delta S that's being added there. Now let's look at the second one. The second one says iodine vapor condenses on a cold surface. So iodine vapors are gases. So we have a gas that's there, and it's condensing. Condensation is a gas going to a liquid. So I can look at my state of matter here. I have a greater dispersal for gases than I do liquids. So what's happening is I'm going to decrease my dispersal of matter, therefore decrease my entropy. So it'll be a negative delta S quantity. So the rule is, when we're predicting the sign for delta S, first look at states of matter. Secondly, if we're looking at states of matter and all of the states of matter are the same, that's when we look at how many moles we have on each side. So hopefully that'll help you guys on predicting the sign for delta S. Now let's go down and talk about how we calculate delta S. You've probably remember seeing this equation before. Delta S of the reaction is equal to the sum of delta S of my products minus the sum of delta S of my reactants. This is known as Hess's law. Okay? The only thing you have to really pay attention to is note right here. Units are in joules per mole Kelvin, not in kilojoules. So make sure when you're writing your answers down that you always look at the data to make sure you have the correct units. Get in the habit of writing down the correct units, because most of the time they will not give you credit if you do not have the correct units written down. So what I'm going to do here is I'm going to take the sum of my products minus the sum of my reactants. Just like with Hess's law with delta H's, I have to multiply by the coefficients. So what I would do here is I would take 2 times SO3's value, 256.6, minus the sum of 2 times SO2's value, 248.1, plus this O2's value. You see how it actually gets a value here. Unlike delta H, it would have been 0. So 205.3. So I take the sum of my products minus the sum of my reactants, and that gives me my final answer. So you can probably try to do this one on your own. You have the answers written down, so you should get a negative 188.3 joules per mole Kelvin value. Now, the question is, what does this value indicate? Well, since this is a negative delta S value, that indicates that the reaction is actually decreasing in entropy. There's a less dispersal of energy that you have as the reaction takes place. I hope this helps with entropy, and I guess we'll talk more when we hit Gibbs free energy.